Alright, welcome back. So this is lecture 6, or part 2 of this, the big 3 set of slides. So we ended right here, and there are two things that I want to talk about that were from this first half of these slides. The first is, and I think they both have to do with copy assignment. So the first thing that I forgot to put, because I stopped typing and it used to not be required, it's still not technically required, is the copy assignment operator's type has a thing at the end of it like const, but it's called no except. So let me at least remember to make a new folder for this lecture. And what I'll do is I'll copy from lecture 5. Yeah, copy from lecture 5. We'll copy the box.cpp and also the make file, and we'll copy that into lecture 6. Okay, so let's go into that now. So we have something to work with. I'll edit the make file very quickly so that we have enough stuff here. This is all from last time. Those don't exist anymore, but we have box.cpp now. So we'll keep that around. And so let's now go back into box.cpp from last time. Dun dun dun. So this is something that will, I think, eventually be required in C++. You have to say no except for your copy assignment operator. And no except in the same place as const, it means that this function cannot throw exceptions. So I guess if you were to have thrown an exception inside of a copy assignment operator, C++ would have to recover somehow, and it just, there's not a way because of what's going on here. So that would mess memory up maybe a little too much, and so it wants you to ensure that you never throw exceptions inside of there. So that's the first thing that I wanted to talk about. And well, let me just show you that that did absolutely nothing because we're not throwing exceptions. But let's pretend we did maybe. And I can say make box because that's the rule in the make file. I could also just say make because that's the first rule that I want to run. And so nothing at all changes. The one thing that will change is if I were to throw an exception, like, I don't know, throw an int, please. You don't have to throw a runtime error. It'll be a compile time error at that point. It'll be like, oh, you just said you weren't going to do that, so no thank you. And the other thing is, I wanted to show you what goes wrong when you don't check for self-assignment. So that's the next thing. So if I say b3 equals b3, and I did not have this check right here that stopped early, let me show you what goes wrong there. And I gotta plug in my tablet. There it goes. Okay. So if we didn't have that self-assignment check, let me show you what happens. So remember the game plan for the copy assignment operator. So what it's going to do, in essence, it checks if we're self-assigning and does nothing in that case. Otherwise, it deletes all of our heap memory and recreates it. A deep copy of the other object that we're trying to copy into ourselves. So if we go to the actual code, you see what's happening. We delete our heap object. It's our one member variable. We delete that pointer so that the space goes away, and then we make room for a new thing and set that thing to the other's value. Okay, so that's the idea. But this all breaks down if we didn't have that check. Because for one reason or another, maybe we're allowed to do b3 equals b3. And once we hit the copy assignment operator in that case, if we didn't have the check, this is what would happen. So let's see what would happen there. So here's my b3. It has a val. And it points to somewhere on the heap. Here's the heap over here. B3 could itself be on the heap as well, but that's beside the point. Maybe it holds 42. Who knows? So if we didn't have the self-assignment check, we were supposed to do nothing, but here's what we'll do instead. We will delete all of our heap memory. Okay, I'm just a computer. I follow directions. And then we will recreate a deep copy of the other object. Oh, but the other object is ourselves, so we're going to say new int, yeah, after deleting. And then we're going to set the value at that heap location to be the other's value. Oh, we're now accessing deleted memory. So at that point, that's an issue. And that is a no-no. It results in something called undefined behavior, which is a scary word, and the compiler, in essence, is allowed to put whatever it wants in place of your code because you're doing something stupid. So if you try to access heap memory, the compiler for C++ is technically allowed to delete your entire hard drive, or to log into Facebook and like some movie that you hate. It's allowed to do that. That's what undefined behavior means. So this is like you're doing something that does not make any sense at all, and so the compiler is even confused. Okay, but it's allowed to compile and run this program. Technically, it doesn't know that you're going to do this. So yeah, just watch out and make sure to check for self-assignment always, because otherwise you're going to try and access deleted memory. And usually, when I say usually, because it depends on the system inside, like it depends on your operating system and everything, this will probably compile and run just fine. Yeah. But you can't count on that. It's undefined behavior. You're accessing memory that does not belong to you anymore. Okay? And that will break one day. Okay, that's all I wanted to say there. So that brings us to recap part 2. We have learned about objects and how they are born and how they live in C++. We have learned all of these different topics. We have a default constructor, and technically we can use it to make something on the heap or on the stack. So this is on the stack. We could alternatively have said for the heap, box star b equals new box. Default constructor. Alright, parameterized constructor on the stack. Alternatively, on the heap, box star b equals new box with 42. You see what I'm doing. Copy constructor on the stack. Alternatively, on the heap, box star b2 b squared b2 equals new box. Now, this one depends. If b was also a pointer, you'd have to dereference it. But let's pretend that b itself was on the stack, so we'll just say b again. And now for copy assignment, that's when you have a box, you declare it, and then sometime later, after its constructor got called, you're going to say b2 equals b. So both of these things have been initialized, and then you're using the actual assignment operator. Okie dokie. And that's separate from something like a different kind of call to the copy constructor, because you can say box b2 equals b, and that's really just another copy constructor call because you're creating b2 at that time. But here b2 has been created, and we want to assign b2 to something else. And alternatively, on the heap, you could just say something like this, assuming b2 and b were both made on the heap, so they're both pointers. You could say box star b2 somewhere over here. And then you just say star b2 equals star b, get at the boxes, set them equal to each other. And then finally, for the destructor, when you have something on the stack, when you have a box made on the stack, once that box goes out of scope, so usually it hits a closing brace, that's when b3's constructor gets implicitly called for you. Okay, so that is when it is on the stack, and it's calling this tilde box function for you. You never have to call this function yourself. Okay, and then if you're on the heap, this is what's going on here. You'll have to declare it somewhere as box star b3 equals new box, like somewhere up here. And then you'll say delete b3, and the second you delete it is when the destructor gets called for you, because you're controlling your own memory there. So yeah, delete is the thing that calls the destructor for the heap objects. So yeah, that is our recap, and now let us move on. And so that brings us finally to this thing called the rule of 3, and I think we discovered it ourselves together. So the point is pointers, and the second you do these things, the second you have dynamic memory, the second you have things on the heap inside of your classes, these default implementations, they do silly things. Remember the silly stuff? And they break down. So the way we fix that is to overload to make a non-default version. So overload just makes a different version. We make our own, roll our own version of these things, the destructor, the copy constructor, the copy assignment operator. But the idea of the rule of 3 is that one's not enough. The second it's not enough for the default destructor to work, most of the time you're going to need to go and overload the copy constructor, the copy assignment operator, etc. And I think I showed you that when I first fixed the destructor. Then we started having seg faults because we then needed to also fix the copy constructor and the copy assignment operator. So it just helps to remember this. It's called the rule of 3. You have to, once you notice you need to change one of those things, you have to change them all, because then that usually means that you're going to have memory problems. Okay, so this is called the rule of 3. What you've been using so far in this class, and probably in CSCI 40, is the rule of 0. And that is, if you don't actually allocate any memory inside your class, C++ will take care of everything for you. So that's the rule of 0. And there's another thing called the rule of 5. And I think we'll get to that at the very end of this class. So there are 2 extra things that are new to C++ 2011. We're using 2017. Those are the move constructor, if you want to look into these, and the move assignment operator. So there's this concept of moving that I guess we kind of touched on a little bit when I showed you returning from a function, returning a class from a function by value actually doesn't call the copy constructor. There's a concept of moving going on here, and moving without having to make copies. And that's the idea of these things. And I think we'll get to those at the end of the class. They're a bit more advanced. But it's all about, at the end of the day, saving work from happening. Okay? That's what these move things are all about. And now you can go forth and implement the big 3 for whatever class you need to implement it for. And the first one that I will force you to implement it for is for vectors. So vectors, at the moment, if we go to our source code, well, they have some issues regarding destructor, copy constructor, copy assignment operator. We're actually leaking memory at the moment in our vectors. So we had a vec, it's called vec, right? Vec v, v dot push back 42, etc. At the moment, from our last lab, nothing is getting reclaimed. All right. When we replace the inner array inside of these vectors, sure, things are happening, but the final array inside of our vectors that we've made for ourselves, those are not getting deleted. Okay, that is a huge issue, because that's a memory leak. Because I can make a loop that looks like this. I can say, I don't know, for just some number, int I equals 0. I hate that this always capitalizes things. I is less than, I don't know, a very large number, I++. And I can say vec v dot pushback 42. So I'm making a bunch of little vectors in memory, and I'm replacing them each time, so they're just making more and more and more and more. The stack memory will be reclaimed, but the heap memory never will be, because I keep making these. Well, here's my v. It's got this array among other things that points onto the heap. And once this thing's scope goes away, once we hit this closing brace and hit the new, we go and execute the body of the loop again, well, this v gets reclaimed, but this thing, this array that it had on the stack with 42 in it, or this array that it had on the heap with 42 in it, well, it never goes away. And the second we make another v, we make another array that has just 42 in it. And so we've lost access to this one, and we do that once every iteration. So eventually your computer will run out of memory if you run this test with your last lab. Okay? That is a huge issue, and we need to go and implement the destructor for our vectors in a certain way. So let us take a look at what we have inside. Okay? So I'm actually gonna, let me take it from the starter code, I guess. Copy / starter code. Oh, I don't have it here. Windows Desktop starter code CSCI 41 lab O. I assume that this is gonna be lab 2. Yeah. And then vec.h. Actually, let me just look at it really quickly. Yeah, that looks good to me. So I'm gonna copy that into my current directory. So now I have a vec.h that we can look at. So this is for your lab. You're going to implement destructor, copy, constructor, copy, assignment operator for vectors. And the one thing that you need to worry about, because the big three, it's all about heap stuff, the one thing on the heap is this array. Okay? The other stuff, they're fine. They're just primitive types. They go away with the vector when it goes away. But this might be set to a heap value, and it will always be set to a heap value. And so we need to worry about that. So in our destructor, here's what we need to do. So we have to worry about our heap memory. Okay, and the only thing we have to worry about then is that array, ARR, okay, which is pointing to a place on the heap. And so when the destructor gets called, that means that this value has either been explicitly deleted by the user, if it existed on the heap, or if it was on the stack, it's being implicitly deleted by C++ because we don't need it anymore. So we have to go and get rid of things. So the destructor only ever gets called when we don't need this object anymore. So we have to delete all of the memory that's associated with it, and the stuff that we explicitly added ourselves we need to get rid of. So we'll delete ARR. And remember, it's delete bracket bracket because it's an array. And that's really all you have to do, because here's our array. It lives on the heap. I had my vector v, I had all my other local variables, or my other member variables that were primitive types. Then I had ARR, which is, I mean, technically a primitive type. It holds a pointer, but the thing there needs to get taken care of. So here on the heap is this stuff, and if the destructor got called on v, that means v needs to go away. Its memory is about to be reclaimed, so v will not exist anymore. And it's our job to go in and delete all the extra stuff. Okay? All the stuff that we allocated ourselves. So as long as we say delete ARR, we will have freed all of the memory. C++ will take care of getting rid of v. We just need to take care of the stuff that we allocated ourselves. All right? So that, in a nutshell, is all you have to do for the destructor. It's essentially one line of code. Not too bad, I don't think. Now the copy constructor, remember the types, remember all those things. Remember what we're trying to do. So we have a vector, and we're trying to copy another one into it. We're trying to make a new vector and copy an existing one into it. So I have a vector v that holds, I don't know, 42 and 43. And then I want to do this. I want to say vec v2 with v. So copy v into v2. That's the idea. And so what needs to happen is, well, we need to make space for that new array, because here's what I have. I have v, and it has its member variables. Actually, I'm going to need to spell them all out this time. We have array, num items, and capacity. Let's do it. I might need to do it over here, actually. Here's v. We have, inside of v, we have array, num items, and then capacity. Let me put the t and the I in the wrong order. T. And let's pretend this was our array. It was like 1, 2, 3. Now, the capacity was, I don't know, we're doing powers of 2, so it's 4. Has to be. Number of items currently is 3. And our array really looked like this. It was of size 4. So, I want to make a new vector called v2 and copy everything in to this. Okay, so it has its own array. It has its own num items. It has its own capacity. And when I mean copy, I mean copy. So these member variables are super easy. I think you know what to do there. If I'm copying v into v2, I need to set this to 3, I need to set this to 4. And that should make sense. But for array, I can't just say, like, inside of this function, it will be called other. V will be called other from our point of view. I can't just say my array equals others array, because that's the default implementation again, which will do this. It'll just copy the address of the starting point of this array. And so now their arrays are pointing to the same place. I change it in v, it changes it in v2, and that can really mess with these things that are supposed to be invariants, not changing. Like suddenly the capacity is really 8 now because I added stuff to v, but I only see it as 4 here. So we need to make a copy of this array, okay? And how big of this, how big should this array that I make on the heap become? It should be whatever the capacity of the old vector is, okay? It needs to also be 4. Okay, so I made my new brand new heap array, shiny and new, And then it's my job to go and copy all of those values in. This 1, 2, and 3, because I'm copying this, I should see 1, 2, and 3 here as well. Okay, 1, 2, 3. And this will be empty because there's nothing there at the moment. Okay, I hope you see that this is what needs to happen inside of a copy constructor to successfully create a new vector called v2 with the same contents as v, but also not being copied shallowly. We're copying it in a deep way. Okay, it's getting its own array. And just to spell it out, let's type this up. So this is the pseudocode for you to go and implement now. All right, so the first thing that we do inside of our copy constructor is we get called with something. As a parameter called other. Okay, so the parameter other is going to be that other vector that we're going to try and copy into ourselves. Maybe I'll put this in monospace font so that it looks like code. So in this case, we're making a vector called v2, and v, the thing that we want to copy in, will be set to other. Okay? So with that, I think it's still going to have that font, so let's change it back. After that, we just need to go and worry about setting our own stuff to whatever others' stuff was. Alright, so in particular, we don't really have to care much about num items and capacity. We can just use the assignment statement for those. Those just get copied using an assignment statement, but array, ARR, needs some work because we're trying to do that deep copy. Oops. So, in order to deep copy this array into this one, I have to first make a new array on the heap of a certain size. How big should it be? Well, it's capacity. It's the same capacity as the other one. So first, step 1, a new array on the heap with the correct capacity. And then 2, sure, now I have that array, I gotta go and copy everything that I needed to copy inside of it. So I need to take all the stuff out of here and put them in here. Yeah? That's how we copy things. And again, other is like the parameter. It's the name of the variable. Okay. So at that point, then we've made everything. Num items and capacity got set, array got set to the right thing. We've made a copy successfully. Okay. Not too bad, I don't think. Copy assignment operator now. So again, the idea is we have 2 vectors now, and they both have been constructed because the copy constructor would have been used if we're constructing one of the 2. So we have like v, vec v, and also v2. And, well, we've pushed back to both of them, possibly. And we should always go for the general case. So let's assume that we have 42 inside of v, actually v dot pushback 43, and maybe v2 has one thing, just to show you the general case when the member variables still differ. And then I go and I say, sometime later, maybe right now, v2 equals v. So this is a copy assignment operator call, because neither of these is being constructed at the moment. They've been constructed already. Okay, well, here's what we would like to happen. Well, let's discover the state of v and v2 at the moment before we make this call. So let's pretend my program's right here. What does memory look like at the moment? I've got v and I've got v2, and they've got, I'm just going to call it size and cap to make my life easier, and then r, of course. So this is what they own at the moment. I've added two things to vec v, so its capacity would have gotten increased to 2, and its size is currently 2, so it's got an array that looks like this. 42, 43. And then v2's size and capacity is 1, which this is the default capacity. We have not exceeded that yet. So this is what the memory looks like at the moment. And remember that I could have just as easily done v2 equals v2, so that's why we always check for ourselves, so that we don't accidentally get rid of the array. Okay, so what I want to have happen now is the following. I'm going to take everything from v and shove it into myself. That's the idea. While copying it, though, so v still gets its stuff. It still gets to keep its stuff. So I'm going to reset size, I'm going to reset capacity, and I'm also going to reset the array after deleting it, right? So we don't want to have this laying around when I reset this to a new place, a new array that looks like this. Otherwise, that would have been a memory leak. So this is what I want, and let's make it happen. So how do we go and implement this? The very first thing we need to do is check for self-assignment. Return early if we're trying to assign ourselves to ourselves. Because in that case, if we naively just followed our plan, we would have deleted our own array and tried to then go and copy from it, which would just have never worked. Okay, so if we got this far, if we're here, it's a different place. It's a different thing that we're trying to copy into ourselves. And all of our stuff is useless at the moment. So we have to delete, and this is going to be the general case for anything that involves heap memory. We delete all of the stuff that we allocated, because we're about to replace it. And in particular, this means that array, this ARR right here, that must go away. So we need to delete our existing array. Alright, and then we can copy all the stuff in again. We can essentially do all of the same stuff as the copy constructor from here on out. We just had to do a few starting things because the state of our memory was a bit different. We had stuff already. Whereas when we're using the copy constructor, we had nothing initially. Okay? So we could just follow the pattern of the copy constructor, which involves copying all the member variables over and making a brand new array with the same capacity and then setting all the values. Alright, so hopefully like this is making sense. Please come yell at me in office hours if it's not. But I want this to be like the most obvious thing to you by the time you leave this class. Alright? Like this is the only way we could have implemented the copy assignment operator, modulo some other things, but this is what needs to happen because of the memory. We've allocated stuff from the heap, we got to take care of it before we copy things over. And we always want a deep copy, so we're going to follow that pattern that we talked about. Okay? How we doing? All right. So now I am going to switch gears a bit into data structures. So we've been talking about one specific abstract data type, and that is vectors. That's what we've been doing in our lab so far. We've spent a lot of time on vectors and how they're implemented. Well, let's talk about your other options in terms of data structures, because inside of a vector we had an array, and we could have put anything there. Why did we choose the array? Maybe we could have put something else that's fancier. Well, these are the kind of questions that you'll be asking yourself late at night after you finish this class. So let me introduce you to all of the data structures we're going to use here, so that you can say that you've seen them and they won't be scary. So first of all, arrays. We've already used these, so I don't really have to say anything else about them. Just a recap, arrays are a place in memory, could be on the heap, could be on the stack, where you have a bunch of things of the same type, right next to each other. And that is a colloquial way of saying these are right next to each other. They're contiguous in memory. So if this was an array of ints, for example, and it started at address 100, I knew immediately that at address 104 was my next index. 108 was my index after that, because every int is 4 bytes. Okay? So that's what an array is. It's just a chunk of memory that you can access each index of, and they're all right next to each other, so you can use that kind of indexing operator. Okay? That's all. That's an array in a nutshell. Now, let's move on to something new. This is called a linked list, and it's kind of like a competitor to an array, and we're going to go over this in a lot more depth. Don't you worry, we're going to go over all of these in a lot more depth, but let me just give you an idea of what this looks like at the beginning. So you can hold a bunch of stuff in order in a linked list. There's a sense of order, like this is the first thing, it's called a node, and then there's this next thing, then after that there's this one, then that one, then that one, then we're done. Okay? And then, oops. There we go. And there's a way to know when we're at the end. There's a special null value, null pointer. But these arrows should make it clear that there are just a bunch of pointers everywhere. So each of these individual nodes, well, inside of a node, it's like it holds one thing, like an int, and then it holds another node. Don't worry if this is very confusing. I'm going to introduce this a lot slower later. I just want to give you the idea. So each of these looks like that and has an address of its next thing, and its next thing, and its next thing. And in order to get to 26, we have to start from first and keep going next forever. So arrays have an advantage over linked lists in some cases. Linked lists have an advantage over arrays in some cases. For example, it's quite easy to add 42 right in the middle. I can just do that. And that's super hard to do in an array because I have to shuffle everything. Okay, so that's a linked list in a nutshell. I know I just checked the time, but I am impulsive. Hash tables is the next thing. So is this my type? No, this is somebody else's type. That is, look at that kerning. That's disgusting. That E is way too close to that K. Don't like that. Okay. Beside that, a hash table is just a lookup table. You can think of it as like a fancy array where the keys in the array are different than the values. So instead of saying like A of I, where I is an int, it doesn't have to be an int anymore. A hash table can take you from strings to possibly more strings, or maybe this is an int. So a hash table can be like this. We can say, I don't know, It's a map that takes string keys to int values. All right, TBL for table. So these are the keys, these are the values. And this is super nice to like look up somebody's phone number. Like, I will go inside of my table and look up John Smith and get to John's, no, sorry, it's this one, John's phone number. Okay, and they're really fast at doing this, even though these are not ints anymore. There's a special way to kind of convert this into an int, and we'll talk about that. So that is a hash table in a nutshell, very quickly. Hash tables are all about speed. For the operations that they support, though. Okay, hash table is a special kind of lookup table, a special kind of an array in a sense. And all right, we've seen a use case for those. Binary trees is the next thing that we'll talk about. Well, this is what they look like. Instead of a linked list or an array where we have a starting point and then a linear amount of stuff after that, there is a branching factor. Like, this is also linear, it's a line, but it might be a little snake or jagged line. There's a bit of a branching factor here. From this root, I have two options. I don't have a next anymore. These are also still called nodes, but they're like tree nodes. I might have some data inside of it. But now I have two options. I can go left, or I can go right. If anything, by the time you finish all your CSCI classes, you will be able to write the most beautiful braces, if nothing else. All right, so, okay. I start at a root, that's my starting point, and then I can go left or I can go right and get more values. And eventually I'll get to the bottom, and then there's like little stopping conditions that involve null pointers, but that's beside the point. Some things that we can do is be able to get places really fast. Like, searching is super fast inside of a binary tree because of this branching factor. If you know which way to go, the bottom is pretty close always, assuming it's balanced, that is. So lookup is quite fast. Or search, sorry. Also to remove as well sometimes. So searching is quite fast here. And it's also, order is important sometimes. And I think we're going to have to wait for me to explain that, but I just want you to have heard these sentences before at least once. All right? So that's a binary tree. There's like a branching factor. You can hold a bunch of stuff. A heap is a special kind of binary tree that we will explore in this class. And, well, what it's going to do is it will be a special kind of balanced binary tree. And it will always have a certain property where a certain maximal node or minimal node is always at the start. It's always at the root. Okay? So, this is an example of a max heap where the root is the maximum node value. And this is really exciting because we can always get the max immediately. It's very quick to find that maximal element. We know exactly where to look. And so when we start talking about computational complexity, keep these in the back of your mind. I'm saying things right now like quick, but what does quick mean? And we'll explore that in a mathematical sense. Very quick to find that maximal/minimal element. Or not find, let's say retrieve. Okay, that is a heap. It's a special kind of binary tree, and in essence, these are the main data structures we're going to explore in this class. Okay, we're going to implement them. We're going to implement abstract data types that use them, and we'll see how fast they are at the operations that these that the ADTs that we make with them support. All right, so that's really the point of this class. We're going to explore these data structures in terms of the ADTs that we can make with them, and these can be actually really, really cool. I'm going to show you at least one example that involves autocomplete, like on your phone. You can just keep clicking, hey, type the next word for me, hey, type the next word for me, and it kind of makes sense. We're going to do that with Shakespeare in this class. So we're going to make our own version of Shakespeare based on a hash table. And yeah, all of these data structures and the ADTs that they support have some kind of operation, okay? Doing something, some operations quickly. They can do them quicker than other things, and sometimes they can do them slower, and there's a trade-off. So it's your job as the programmer to pick the best data structure, or usually combination of data structures, for whatever you're trying to make, for your purpose, for your programming assignment. And this will follow you forever. All of the, like if you're trying to get a job in an industry, for example, one of the most common questions is data structures and algorithms questions. Okay, that's the most common type. And I'll be showing you a bunch of different examples and of all these different kinds of complexities that arise from the operations that we can perform on these data structures. Okay, so again, the goal of this class, hands down, let's make the colon bold as well, is to learn how to combine these data structures, how to use them together to solve whatever problem you're looking at. And usually there's going to be just one obvious choice, or maybe we have to try a few options. But it's all going to come down to efficiency, and that's why in the next set of slides, we're going to talk about computational complexity in detail, and how to measure it, how to talk about it mathematically. And so that'll be what we keep thinking about, what we keep coming back to when we talk about all these ADTs and data structures that we talk about in this class. So that was a lot of words, not enough programming, I know, but that is something that I wanted you to see so you know where we're going. All right, so let me check the time. And yeah, I might let you go a bit early today. So let's talk about some exercises first. I think I might, yeah, let's start with this one. That's fine. So what I want you to do is update the box class that we talked about. I know it's not the same one as your first lab. Sorry. It's a box that holds something this time. Update it to hold 2 things instead of 1. Okay? And those 2 things should be held on the heap. And this will be great practice for what you're about to do in your lab. So update the implementation of that copy constructor, the copy assignment operator, the destructor, so there are no more memory leaks anywhere. Okay, that's the idea. So now you have 2 things to keep track of inside of your box. If I make a box B, I don't know, maybe it'll hold 42 and 43, and it's 2 objects. All right, so on the stack, maybe I made B, and it held its val 1 and its val 2, let's say. And these are both on the heap. So, I don't know, let's put the heap over here. Boop. Boop. So it'll be 42 and 43. How does this change? Well, the destructor, for example, needs to delete an extra thing. The copy assignment operator also needs to delete an extra thing before it copies the new stuff in. The copy constructor and the copy assignment operators both have to copy a new value after making space for it on the heap. Making ROM for it. And you'll also have to update the constructor as well. Maybe you'll add some new getters, some new setters, but that's kind of the idea. And yeah, try testing that out. I think that'll really help as you think about the big three before you think about it in terms of vectors, which might be a lot at the moment. But please think about that and come yell at me in office hours if you have any trouble with it. The next thing, try to come up with an example program idea that would benefit from arrays. All right. So remember what they're good at. They're putting stuff next to each other. Probably pretty simple for you to think of just a toy program that would work well with arrays. I want you to start thinking, like maybe look up in your book or on the internet, on Wikipedia, there's good pages for all of these things. Try to think of some examples that would benefit from linked lists, binary trees, heaps, and hash tables. I told you at least one good thing that each of these are good at, but try and generalize. Heaps don't have to hold ints, they could hold strings. As long as there's some kind of property that's maximal or minimal, they can hold that. So heaps can hold, for example, strings, any other type. And that's actually true for all of these. Okay? Try to think about that. I think that would really help you. And in a future lab, I'm going to ask you to use the implementations of ADTs that involve these things, just from the C++ standard library, and you'll get some experience with that. So I think that's where I want to leave you today. Do some extra research if you're interested. Try this out if you want. And yeah, talk to me if you have any questions, but good luck. Your lab will be exactly this, implementing the big three for vectors. And hopefully I've given you enough clarity to get that done. But please talk to me if you need to. And I think that's where I want to leave you. So good luck with that, and yeah, I will see you next time.